Welcome to the second lecture of chapter 3. Today we're going to cover the second part of metal complexation. This is basically a more advanced version of what we talked about, or more comprehensive version of what we talked about in the first lecture. So the basic, it would be pretty much the same, except the fact that we're going to work on a wider range of ligands. In the previous lecture, it was either H2O, water, or hydroxide. But now we're working with carbonate, for example, with ammonia as also the ligand. So it adds a little bit of complexity because they are part of acid-base, or it could be a part of an open system. So you see that soon. We're going to also construct the PC-pH diagram and also solve for speciation, specifically for solution pH. So quickly overview what we talked about. It was a very straightforward reaction. If we have a metal in the system, a big chance that we have a complexation reaction, which is basically a ligand with the metal forming the complex. And for the ligand itself, in the previous lecture, we covered water and hydroxide. But here we're going to talk about more ligands. Also, we introduced a few designations to describe the equilibrium of a complexation reaction. For example, we introduce metal plus IL forming the complex, or the complexation reaction could be written in a IHL, the protonated form of the ligand. So it would be metal Li plus proton. Or it could be written like stepwise. So this could be, for example, MEOH plus hydroxide as the ligand to form MEOH2. Or the same thing could be written also as stepwise in the protonated version. So MEOH plus H2O forming the metal OH2 plus H plus. So either of these four could be like standard approach to write a complexation reaction, but each corresponds to a specific type of equilibrium designation we talked about. Anyone on the first reaction? The pure metal plus I ligand. So this was basically beta I, and the protonated version was basically beta star. Anyone for this specific reaction? Is it beta or K? It's K, so it's a stepwise. And what's the step here? So we are making the second one. So this would be the second step. So K2. And also the same thing for the protonated version. So this would be K2 star. So this is what we covered in the previous lecture, but now we're basically working on this ligand, making it a little bit more comprehensive. As you see, when it's comprehensive in terms of acid-base, that means we have to bring some of the calculations from chapter 2. And when it's an open system, we have to also bring some of those information from a lecture related to gas-liquid equilibrium. So as I mentioned, complexation can happen, not just by water and hydroxide, but also other ligands. Some of them are more specific, like this one, for example. and some of them are a little bit more comprehensive. Like as I mentioned, hydroxide and water are basically for pretty much all kinds of uh, metal. So previously we mentioned that the metal is in aquatic system always complex with water. So when it's metal ion, it's always surrounded by molecules of water. But sometimes if we introduce a stronger ligand, then that would be some of the water molecules will be replaced by the molecules of the new ligand, stronger ligand. So this kind of reaction, we call it ligand exchange reaction. So we're going to see that experimentally also in the last lecture, like in the lab, adding step by step, adding a stronger ligand from the metal with just water around it, then basically going for, let's say, ammonia and then EDTA. So, but the reaction itself is called a ligand exchange. So if we have, let's say, metal surrounded by X molecules of water, let's say this is N plus, then we introduce a stronger ligand, for example, ammonia. Then we get metal with one less water plus ammonia. And this would be still N plus charge because ammonia is not changing that charge of the species, plus one molecule of water. So basically what happens is one molecule of water is replaced by one molecule of ammonia. A ligand exchange happens. And this is because ammonia is a stronger ligand than water. So for this kind of reaction, which is probably, you see that very often, we normally remove that water part. So we commonly write this as metal N plus plus ammonia to form metal ammonia. This would be N plus. So this is a very known reaction, ligand exchange, in the context of complexation reactions. So if you have something stronger than ammonia, if you add it, that would replace water and ammonia. So again, the complexation reaction proceeds. So the same designation we used for hydroxide, that beta, K, everything, is basically applies also with other ligands. For example, if we're dealing with ammonia, with zinc, then zinc 2 plus 3 ammonia, which would be zinc ammonia 3 2 plus. This would be beta 3, like the same beta 3. So we look for beta 3 in the table. Or if we have something like zinc with 2 ammonia, and adding one more ammonia, then this would be the same K kind of designation. So still very similar to what we talked about in the previous lecture, we extended to a different ligand in this case, which is ammonia. So the second topic is basically mixed ligand complexes. So sometimes we have metal formation, metal complexing with more than one ligand. For example, if we have, let's say, a specific metal in the solution, let's call this MEN plus, Then this metal, if it can complex with chloride and also ammonia, then by adding ammonia and Cl minus, then you get basically the ligand exchange with both ligands, resulting in a complex ligand. So MEH2O, as always, is surrounded by water. Let's say X. N plus is the charge. Then adding 1 Cl plus ammonia. What would be the complex if we get both of them, or we replace both Cl minus and ammonia with water? Or opposite? What is it? But still we have some water. So let's say we're not removing that water from the notation. How many waters we got now? X minus 2. And then ammonia, then Cl. And what's the charge? Exactly. So ammonia doesn't have charge, but Cl is -1, so this would be N minus 1. And then it releases 2 molecules of water. So basically the same ligand exchange happens, but this time with 2 ligands. So here, this is basically called a mixed ligand complex. So we have more than one. So the good news here is that we are not going to consider any mixed ligand in this course. So it's always about one ligand. So it by itself could be comprehensive, so we don't want to mix them together. But in reality, you get those sort of mixed ligand. So the other important topic when it comes to complexation with other ligand is basically chelating agent. If the complexes are very strong, they're called chelates. So that ligand is called chelate, and then, or it's called the chelating agent. So the complex itself is called chelate. The ligand is called chelator or chelating agent. So the most commonly known chelating agent is EDTA. It's basically, this is the EDTA. It's a tetraprotic acid. So if you work in analytical chemistry, EDTA is a pretty known molecule. It chelates very well. And here, for example, I'm showing this molecule is EDTA4 minus, so the most or fully deprotonated version. Just fully deprotonated version of the ligand. In this case, is also a chelating agent. And EDTA complexes very well with many metals. So in this case, for example, we're showing Pb2+. So this is the center is lead, and then this is a complex of lead with EDTA. So Pb with EDTA, and the charge would be 2 minus basically. So as you see, this has 1, 2, 3, 4, 5, 6 bonds from 6, forming 6 bonds. So it's very strong. The chelating agent is very strong. So it forms 6 bonds, which is very strong then. So if you have let's say, a water sample that contains lead, and you want to get rid of lead because it's very toxic, if you have options between ammonia, Cl minus, and EDTA, obviously EDTA would be more effective in terms of the complexation reaction. It's very strong, so then you can effectively remove lead from the solution. And in this case, your approach in terms of the separation could be based on charge because lead by itself is 2 plus, but then you're forming a a negatively charged species, then you can basically doing some ion exchange to be able to remove it. Just an example. So EDTA is very strong. It forms this chelate, and then this is basically a chelating agent. So this is by itself is a very broad topic. It has so many dimensions, bidentate, for example, kind of chelates, but here we just want to introduce it and then say this is probably not what we're covering also in terms of speciation. So we're not going to deal with something like EDTA, but rather mostly with ammonia and other species, other ligands. So the previous table that I showed you was qualitative information about what kind of ligand, each ligand, how they complex what kind of metals, but no information about the equilibrium constant and up to how many they can complex. For example, when it comes to the other table was telling me ammonia would complex with copper, but how many steps or how many K values, we don't know. But this table is one of the most important table in this chapter. What it shows is first each metal, the complexation with each ligand. So this would be basically the metal. And this would be all the ligands. So for two things, it shows, for example, Ag and CO2 doesn't form any ligand. That's the first information. And if it does, up to how many, for example, in terms of Ag and ammonia, it shows it proceeds up to 2 ammonia. So 1 ammonia with Ag and then 2 ammonia with Ag. The third layer of information is basically the actual value. So in this case, it's showing the beta value. So the actual beta value for this reaction would be this one. So as you see, some metals go crazy in terms of like the complexation with ammonia, like cobalt up to 5, for example. And cobalt is pretty active in terms of fluoride or, for example, sulfate and carbonate. So if you have cobalt in the system and any of this ligand, then you're potentially having all of this species. So you're expecting to have that. So this table gives you that whole perspective of what you're expecting and then the actual equilibrium constant. So this is a very important reference for homework also. Sometimes one way is to look at the table, but just make sure that the question that you're asked, it's not simplified. So sometimes they ask you, oh, this ammonia, this cobalt with ammonia, just consider up to 2 ammonia. So just these 2. So just sometimes we simplify it for the sake of calculation. So that would be it for complexation. In this lecture, we just highlighted a little bit more diverse on the ligands. Also introduce a little bit more on some of the terminologies, like mixed ligand, and then also the chelating agent. But the concept of calculation would be very similar, would be basically the same as what we had in the previous lecture. So here we're going to solve 3 questions. And as you see, these are basically bringing some of the concept we've learned in chapter 2 and connecting it to chapter 3. So, but the chapter 3 part would be similar to what we had in the previous lecture. So the first question is about mercury in a lake. So, mercury could be toxic, it could be dangerous. So monitoring mercury would be something very, very important. So here the information that is given is we know the total amount of mercury. So we know later we need this for mass balance. It's 10 to the minus 5. We also know that in the lake, we have low concentration of chloride. So the total Cl is 10 to the minus 3. So we're expecting sort of a complexation between mercury and chloride. And also the information that is given is that Hg2 plus can react with up to 2 hydroxide ions. So that's another ligand that we have to be worried about. So, and also we have the quantitative information for complexation with hydroxide. the beta value for 1 and 2 is given, and the complexation for Cl, the 1 and the second one is given. So we know the quantitative information. And assume no precipitation and no mixed ligand. So the no precipitation assumption, we're going to revisit it in the next lecture, but the no complexation is beyond this course. So no mixed ligand complexation. So we want to construct the PC-pH diagram, and also if the lake pH is at 6, we want to see what's the dominant Hg species, because different entities of Hg might have different toxicity. So we want to sort of indirectly evaluate the toxicity of the water from the lake. So as you see, this is very similar to speciation question we had in chapter 2. Normally, we start from species. So we start from what kind of species we have, then we go for equations. But here it's easier to start with equations, because equations would tell you what kind of species you have eventually. So it would be easier for this example and for the following example to start with equations. So the very first equation is basically the first complexation of mercury with Cl minus. So that information is given. You also can go back to the table to see if, Hg is not here, so never mind. But if the table was telling us up to 4 Cl minus, then this example is specifically limited to 2. So, but we know it happens up to 2, and the beta value is given. So when beta value is given, it depends on, it would be basically the beta notation for the standard reaction. So we know Hg2 plus 1 hydroxide. Sorry, first let's write it for hydroxide. Then it would be HgOH plus. The charge balance is there, everything is there. The charge balance in terms of the species, I'm saying. So we know beta 1 of hydroxide would represent this reaction. So this would be HgOH plus, Hg2 plus, and then hydroxide. So this is how the species are basically related to each other. That's the first equilibrium, or the first equation. The second one is, again, is beta is given. So Hg2 plus 2 hydroxide. You would get HgOH2, and this is represented by B2 of hydroxide. Give us HgOH2 divided by Hg plus 2 plus OH minus to the power of 2. And this is relationship 2. So hypothetically, if Hg would undergo more than 2 hydroxide, you basically just expand this more and more. It doesn't add a layer of complexity, but it adds more species to your system. So the second type of complexation that might happen, because we have also Cl minus, is the complexation of Hg2 plus with Cl minus. So HgCl plus, and this is represented by beta 1 of Cl, FgCl plus, Hg2 plus, Cl minus. Relationship 3, and then this proceeds up to 2Cl. Keep in mind this HgCl2 is still in the aqueous phase, it's not a precipitate. Beta 2 of Cl, this would be HgCl2 divided by Hg2 plus, and then Cl minus to the power of 2. Any other reaction we have? Cl minus is not a part of an open system. It's not a part of acid base. So no more reaction, except like water is always there. So water dissociation, H plus, that's, don't know what happened there. H plus plus OH minus. And this is KW is basically representing this reaction. So now we have all the possible reactions that could introduce species to the system. And now we can talk about species. What are the species beyond H plus and OH minus? Hg2 plus. AgOH plus. Exactly. So HgCl plus and HgCl2. Anything missing here? Exactly. So Cl minus could also be a part of the speciation. Can we write charge balance? So we have yes and no. Why yes? Because I'm also on the no side. I just said I'm on the no side. If we have what? Exactly. So similar. So you're no then. Okay. So we're on the same page now. So you know how much total Hg2 plus you have from the mass balance, but you don't know how it's introduced or what's the anion of that one. So you're not allowed to use charge balance, but because probably that Hg plus was introduced by something like HgXN type of salt. So you don't have information about that X. It might be so many other ions also in the system, which is not given. But here we're just we have the information about the mass balance. We don't need, yep. Exactly. We don't know how that Hg2 plus, because Hg2 plus cannot be introduced by itself. It has to be introduced accompanied by an ion. And we really don't need charge balance as long as we're not going to calculate pH. So here we're not able to calculate the pH of the lake. That's it. But we have the mass balance. So the mass balance, here we have two types of mass balance. Not two types, mass balance for two species. What are the first mass balance? That's the first one is for Hg. Then the total Hg. What would it? Yep. So this would be 10 to the minus 5 molar. And what are the species? Starting from the simplest. So Hg2 plus. Then all the other Hg's basically. HgOH plus. Hg2OH. Also HgCl plus plus HgCl2. So all of the species would give me Hg eventually. Or all the Hg that was in the system is a combination of all of these species. And each is introducing 1:1 kind of ratio. What is the other species that we can write mass balance? Yeah, total Cl. What's the value? 10 to the minus 3. So before we write the mass balance, just compare the two values. 10 to the minus 3 versus 10 to the minus 5. So we have 100 times more of the Cl compared to Hg. We're going to use that later, but just keep in mind the differences between the two. So what is the mass balance here? Cl minus. What is missing here? Cl2 gas? No. Something is missing in this line. We don't have any other species that contain Cl, right? Only Cl minus and the two complexes. One molecule of Hg2 plus would give me one molecule has one contribution to the total mass balance. HgOH also has one. Exactly. So one molecule of HgCl2 would give me two molecules of Cl minus, or the molar ratio is 1 to 2. So whatever concentration of HgCl2 I have, 2 times of that has the contribution on the mass balance of Cl. So again, it depends on what kind of mass balance we're talking about. Here is the Cl mass balance, so we only care about Cl part of the molecule, which in this case is 2. So now we have the two mass balances also for equilibrium. I mean, plus water would be 5. So now what we want to do is basically converting everything to Hg2 plus, like what we did in the previous lecture, and then use this equation to be able to look at the speciation. Again, we don't have the information about the whole picture, so we can't do charge balance. So from equation 1, I can rearrange it. So it gives me all the other species, it has to be converted to Hg2 plus. So this would be beta 1 OH, Hg2 plus, and OH minus. So this looks like a good relationship because HgOH plus is a function of either Hg2 plus, something that we're interested to have, and also something that is pH dependent. So this is sort of a very good expression to have. Similarly, if we proceed with number 2, then this would give us HgOH2, then beta 2 of OH times Hg2 plus, and then OH minus to the power of 2. So this is also pretty good. So now working with relationship 3. So this is exactly what we had in the previous page. So these are basically corresponding to this reaction. We're just rearranging it, simply rearranging it. So this one, we want to rearrange it in a way that we somehow have an expression for HgCl plus. So then here would be HgCl plus equal to beta 1 Cl, Hg2 plus, and then Cl minus. So this one, it seems, is not the best simplification of HgCl plus for one simple reason. At each pH, we really don't know what's the Cl minus, specifically the Cl minus composition or concentration. So this term obviously is pH dependent because it's connected to the whole matrix of species. But we really don't know what is the value here. So we need later expression for Cl minus as a function of pH if we want to rely on this expression for HgCl plus. So for now, let's say this is not the most useful expression. So we want to do the same thing for number 4 to figure out what is HgCl2. Then here this would be beta 2Cl, Hg2 plus, then Cl minus to the power of 2. Again, this is not something that is directly useful. So now that we have all the expressions for the individual species, we can put it into mass balance for Hg. So the next step would be 5, 6, 7, and 8 into total Hg mass balance. So the total Hg would be Hg2 plus times 1 plus beta 1 OH, OH minus, plus beta 2 OH, OH minus to the power of 2, then beta 1 Cl, Cl minus, plus beta 2 Cl, Cl minus to the power of 2. So let's call this relationship 9. So in the previous lecture, we had the relationship up to here. And this was very useful, very straightforward. At each pH, we have the OH minus value. These are the constant. This is also constant. We could quickly calculate Hg2 plus at each pH. It was very straightforward. But now we have also this term. Specifically, we have the Cl minus term. So we need a separate calculation at each pH to first figure out what is the Cl minus concentration, then putting into this expression to get Hg2 plus. Once we get Hg2 plus, then we put it into this 4 to get all of this species, right? To get to Cl minus, then we need to work with the mass balance of Cl minus. So the other expression we have. So we can put 7 and 8 into the mass balance of Cl. So what happens is basically total Cl is Cl minus 1 plus beta 1 Cl H plus, sorry, this is not H plus, this is Hg2 plus, plus 2 times beta 2 Cl Hg2 plus times Cl minus. So now if you look at it, this is basically a set of equations. Two unknowns, Hg2 plus and Cl minus at each pH. Because when you say at each pH, this is known. These are all known. This is unknown, and this one is unknown. The same thing here. These are unknowns. And you see this is like basically a nonlinear kind of equation. So one way is at each pH, you have a programming language, let's say, and you solve for Cl minus and Hg2 plus. So that would be sort of a comprehensive calculation at each pH. Once you have this one and this one, then you can basically go up and calculate all the other species. So that would be one way. So let's rearrange this a little bit slightly to make it Hg2 plus kind of thing. Then this would be total Cl minus Cl, just rearranging it a little bit. Beta 1 Cl plus 2 beta 2. So this was one step to a little bit simplify it in terms of not to solve for the set of equation, but just replace the Hg2 plus by this expression. So basically what happens, you get one equation, one unknown, and non-linear. So mathematically speaking, this could be solved by, for example, equation 10 into 9. What happens is then we have Cl minus as a function of known parameters. Which is basically beta values, the total values, and the pH. So then what we do is basically for each pH, we need to solve a polynomial equation. So for each pH, we can solve for all the species and eventually PC-pH diagram. So this cannot be done by Excel because the previous case, it was very straightforward. Each column was related to the other column, and then it was just basically solving like directly. But here, at every single point, you have to solve a polynomial equation. So it requires a little bit more to be more aggressive on the calculation using something like MATLAB or Python. So, but it's doable. One equation, one unknown at each point. But here we can make a very good assumption to simplify the calculation. If you remember, the concentration of Cl minus is significantly bigger than Hg2 plus, 100 times more, right? So we saw that. So let's do first. Assumption based on the fact that total Cl is way bigger than total Hg. How we can use this assumption? What does it mean? This might be a very tricky question. But to answer that, we can look back at the total mass balance of Cl specifically. Cl minus, the total of Cl is way bigger than the total of Hg. What does it mean in terms of this specific? How we can simplify this? Exactly. Why is that? What's the justification? Exactly. So the point is, assume all Hg is consumed by Cl minus, all of them, or a combination of Cl plus and Cl2. Still, that contribution, max of that contribution would be 10 to the minus 5 from the mass balance of Hg. And then 10 to the minus 5 plus something is 10 to the minus 3. So we can assume, it's a very fair assumption to say total CL is equal to CL minus. So if we have that assumption, that would makes it very, very simple. So then this would result in total CL, concentration of CL minus, which is 10 to the minus 3 molar. So now if we have that assumption, what happens is that then the Hg2 plus, this factor is gone. So we can go back to this one, and now we have something that is as a function of pH, or something that is always constant, not pH dependent. So basically this would be similar to the previous lecture, that we have a pH dependent term now plus a constant, and that constant is basically this one, which doesn't change because this concentration doesn't change, this doesn't change, and these are constant basically. So, and this is a very justifiable assumption. Later you have to check it. You have to basically calculate the concentration of Cl, but then this was very justified. So if we do that assumption into expression 9, then it would be very simple and straightforward. Then in that case, Hg2 plus would be total Hg divided 1 plus, similar to the previous lecture, beta 1 OH and times OH minus plus beta 2 OH, OH minus to the power of 2 plus beta 1 Cl, total Cl, plus beta 2 Cl, total Cl to the power of 2. And this would be expression number 11. And this was a clear example of how a good assumption would makes it very straightforward and very easy for solving the speciation. Again, once you have Hg2 plus, you can calculate for all the other species based on the relationship 5, 6, 7, and 8, because that would be a very simple expression for each individual equilibrium. So now what we need to do is we solve for Hg2 plus, the concentration, using equation 11, which is as a function of pH. And then we calculate other species using the other equations 5, 6, and 7 and 8. So if we go to that Excel file, you see that it's very similar to the previous case, but now we have 2 or 3 more columns related to the presence of Cl. So Hg2 plus, and as you see in the formula, it's basically a function of a pH dependent factor and also a constant. Then once you have Hg2 plus, calculating this 2 would be using beta 1 and 2 for OH. This is, as we mentioned, this is always equal to the constant, the total Cl minus, the mass balance of Cl minus. And then these 2, you can you need to calculate it based on the concentration of Cl and also Hg2 plus. And as I mentioned, we don't have any information about the charge balance, so we're not allowed to use the charge balance expression. So this would be basically what we mentioned. And then we can also check the assumption that we made, the combination of this one plus 2 times this one, would be still very, very smaller than this guy. So the major part is basically a Cl minus. And this is basically the speciation. As we were expecting at a higher pH, more hydroxide, we start to see the hydroxide dominated complex, like this one, like this one. But as we go down in terms of pH, the Cl plus or the Cl2 is basically the dominant species. The second part of the question is asking us what's the dominant species at pH 6 of the lake. What is the dominant species? I mean, the mercury containing species. Exactly. So HgCl2 is dominant. So again, this kind of information, or the species pH diagram, would quickly tell us what's the dominant species. So if we worry about Hg2 plus, mercury ion, then it's very negligible in this lake at pH of 6, because this would be the concentration, 10 to the minus 13, for the total concentration of 10 to the minus 5. So just a very tiny fraction is in the form of Hg2 plus. This is mostly taken by Cl2. So if this is poisonous to the biosystem in that lake, we don't need to be worried about it, because most of it is complex with Cl2. Just an example. Okay, so what we did was a PCPH kind of diagram, constructing based on sort of a complexation with 2 ligands, not 1. And we made that very useful assumption to simplify the calculation. So that was basically what we did. So the second example is chromium in water. Again, another important metal. But this time we have more information. The first information is that we know how chromium is added. Chromium is added by chromium nitrate salt, 10 to the minus 4. Then the sample is exposed to pure ammonia gas phase. What does it mean? Like, let's decode this sentence. No. This part we can use charge balance for sure. You're right. But what this part means? Exposed to the gas phase. You answered that in the previous question. Exactly. So it's an open system now. It represents the actual environmental system. Let's say the lake is out there. But this is a very specific system, because the gas phase of ammonia at 1 atmosphere is not, you don't see it in in the nature. It's mostly a controlled chemical unit. And we're giving the pKa of ammonia, also the partial pressure of ammonia, and also the Henry's constant of ammonia. So this beaker has chromium nitrate exposed to ammonia. So we're expecting to have acid-base reaction complexation and also the open air kind of gas liquid expression. So this is one example that combines what we've learned in this chapter and also the previous chapter. At the end of chapter 4, we make this more comprehensive by adding also a redox reaction, also potential precipitation. So this would be the most comprehensive example that you see at the end of chapter 4. But here we're ignoring all the complexation of chromium with hydroxide, again, for the sake of simplicity, but you know how to deal with 2 complexes, previous example. And we're also ignoring mixed ligand complex, and also we're ignoring the second complexation with ammonia. Based on the table, chromium can extend up to 2 complexation with ammonia. So chromium with 1 ammonia, chromium with 2 ammonia. And we have the beta value in the table. But we're basically, for the sake of calculation, we're also ignoring that part. So the first one would be. Now we want to calculate the solution pH. The salt is added. If you add the salt, we know this is Lewis base. So this pH is less than 7. But now we're exposing to the ammonia atmosphere. So maybe the pH goes beyond 7. We don't know. We need to do the calculation. So again, it's good to start with equations and then to see before we do the speciation. So the first equation, it's basically the exposure of the gas phase. So when you have ammonia in the gas phase, from chapter 2, we know that it equilibrates with the aqueous phase. And basically the Henry's constant represents this equilibrium. HPM is given. So HPM, the expression is basically the partial pressure of ammonia in the gas phase and then ammonia in the aqueous phase. So now we brought, up to this step, we brought ammonia to the liquid phase. Once we have ammonia in the liquid phase, immediately we have to consider acid-base reaction of ammonia. So acid-base reaction of ammonia in the standard form would be ammonium and ammonia. And then this is represented by Ka. Ka represent this reaction. So this would be ammonia in the aqueous phase times H plus divided by ammonia. So obviously ammonium is also in the liquid phase. So I'm not writing that notation here. So this would be relationship 2. And the Ka value is also given. It's 10 to the minus 9.25. So now that's all about ammonia. We introduce ammonia by exposing to the gas phase. We also introduce chromium to the system by dissolving the salt. So what happens is chromium nitrate is dissolved. So one-way reaction is basically dissolved. For now, we're not basically dissolution and precipitation, we're not considering. So this would be basically, it fully dissociates to the chromium 3 plus 3 nitrate. And once we have chromium 3 plus in the system, we know obviously this chromium 3 plus is surrounded by X molecules of water. For the sake of simplicity, we just remove that part. We know once we have ammonia, we have ligand exchange. In this case, 1 molecule of water with 1 molecule of ammonia. So what we get is basically with ammonia and then chromium ammonia, the charge would be still 3 plus. And what describes this one is basically beta 1, which is, and something that I have to write. This is basically the aqueous form of ammonia. So just keep in mind, this is the aqueous, the one that is in the liquid phase. Chromium ammonia, 3 plus, and then chromium 3 plus 1 ammonia. Again, this would be aqueous. I'm not going to write this aqueous anymore, but from here, it's all about aqueous species. And this is from the table. The value is from the table. We can get it from the table, which is 10 to the power of 4.4. So this would be relationship 3. And as always, we have also water. And this is Kw that represents this one. So we have the whole picture. We can also write down the species. Have H plus, OH minus. We have, what else we have? Let's start from the top, like the reactions we have. Yes, NH3, aqueous, obviously. We don't care about the gas phase because it's all speciation about the liquid phase. What else? Chromium. Well, chromium nitrate. It's only, yeah, that's the solid phase. So let me put this S here to show this is a solid phase. So we don't care. We don't care about it in this lecture, but the following lecture, the following two lectures, that's actually the whole precipitation distribution. So chromium 3 plus, chromium ammonia, and nitrate. So we have all the species. Since we know how the species are introduced, we can also look at the charge balance. Anyone for the charge balance? Mm-hmm. Mm-hmm. Chromium, like, yep. So that's what's missing here. Exactly. So this guy is introducing 3 times of the charge. So 3 times the concentration is how much of the absolute charge is introducing, and also the same for this guy. So correcting for the, not correcting, including the charge of the species. So we can also look at the mass balance also. We know the mass balance of the salt. So we know how much salt we added. And initially we know it dissociates to chromium and nitrate. So we can write mass balance for both chromium and nitrate. So the total chromium, what's the concentration? Is equal to the concentration of the salt, which is 10 to the minus 4 molar. And what are the species? Mm-hmm. 1 times chromium 3 plus. Yeah. Anything else? No. Okay. So that knowing the concentration of the salt, that gives me mass balance for 2 different elements, chromium and nitrate. It doesn't need to be like, you mean, why not including 3? Oh, yeah, that's, I mean, I'm not using charge balance for solving the pH now. I don't want to mess with this one. So we have a long time to go. So, but you're right. This is actually the key equation. So for, let's say for total chromium, what's the total nitrate, the concentration? Exactly. 3 times the concentration of the salt, or 3 10 to the minus 4. What are the nitrate containing species? What else? That's it. So, but the good thing is we have immediately the concentration of one of the species in the charge balance. This is pH dependent. Obviously, these 4 are pH dependent. We just need to figure out how to calculate that. So here it seems is relatively straightforward. We take mass balance as always, mass balance, and then we try to convert every concentration into chromium 3 plus and something that is either pH dependent or something that we know. So here we can do 3 into 4. What happens is that the total chromium would be chromium 3 plus beta 1 chromium 3 plus times ammonia, obviously in the equilibrium. So this is good, but not good enough, because we have chromium 3 as a function of a known, something known, but something pH dependent. So the next step is basically to write something for NH3 plus as a function of a constant and also a pH dependent factor. What's the best one to use out of the 6 equations we have? What's the easiest one? What's that? So 3, you got this one, but you're bringing also this to the table. Something simpler. What's that? Exactly. So this one. Because this is a function of a constant and a constant. So the partial pressure of the gas and also the Henry's constant. So basically, if we do 1 into 6, then it would be pretty straightforward. Total chromium is chromium 3 plus times 1 plus beta 1 P of NH3 in the gas phase, HPM. So now we have chromium 3 plus concentration as a function of constant, 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 also constant. So chromium 3 plus concentration is not pH dependent, basically. It's similar to open system. If you remember, carbonic acid concentration wasn't pH dependent. It's always equal to H. It's always a function of the partial pressure and Henry's constant. The same thing here for ammonia. The concentration of ammonia is always constant. It seems chromium 3 plus concentration is always constant. It's not pH dependent. Okay, so now we have the last relationship. It seems we have all the information to insert the actual numbers. So what we have is basically the concentration of chromium 3 plus is equal to the total 10 to the minus 4, 1 plus beta 10 to the power of 4.4 times the partial pressure in atmosphere 1, and then the Henry's constant, which would be 0.0171. So again, this is basically the total. This is HPM. This is beta 1. And if we actually have calculate for chromium, this would be 6.8, 10 to the minus 11 mole. So now we have chromium 3 plus. The rest would be just straightforward. We go backward, put it into other appropriate equations, and then calculate for each individual species. So for example, into relationship 3, it gives me chromium ammonia concentration, which would be 10 to the power of 4.4, that beta times chromium 3, which is 6.8, 10 to the minus 11, times HPM, P1 divided by 0.171. This is 9.9, 10 to the minus 5 molar. What does it say, like comparing these two numbers? So this is significantly bigger, right? And this is very close to 10 to the minus 4. So almost all the chromium, the total chromium, is in the form of the complex. So, and chromium individual species are basically a combination of these two. So it's almost total chromium is equal to chromium ammonia 3 plus concentration. So now we calculated this one. The next thing would be basically put everything into charge balance, because we want to calculate the concentration of H plus or calculate the pH. So all into charge balance. So what we get is H plus, something we want to calculate, plus 3 times chromium 3 plus 3 times chromium ammonia, plus ammonia plus hydroxide plus nitrate. So based on what we've learned up to this point, we can basically a little bit simplify this one. Obviously, this is a one equation, a one unknown. We can simply calculate, but to a little bit simplify it, we know this one is almost equal to 0. This is almost equal to total chromium. So this term would be 3 times the total chromium based on what we just learned. This is basically based on equation 2. We know it's ammonia times H plus divided by Ka. And we know this ammonia term is equal to P of ammonia divided by HPM. So we convert this term into a pH or H plus term. Hydroxide, this is Kw over H plus. And nitrate, we know this is basically 3 times the concentration of the salt. Three times the concentration of the salt is equal to 3 times the total chromium as well. So, because the salt was equal to the total chromium, so 3 times salt. So as you see, this will be cancelled by this one. Just a little bit of simplification. So if we rewrite it a little bit, so then this would be H plus 3 times total chromium plus PaNH3 HPm H plus Ka equal to Kw over H plus 3 times the total chromium. So this would be cancelled by this one. We can multiply this by H plus to make it a little bit more straightforward, and then rearrange. Eventually we get something like this. H plus would be Kw over 1 plus PaNH3 HPm 1 over Ka just to the power of half. So and we have literally every single parameter here. 3.1 10 to the minus 13. So here, as you see, pH is not, it's just depending on the concentration of the gas or the partial pressure of the gas. And it's very alkaline. So exposure of that gas phase was basically the key to dictate the speciation, specifically the H plus or pH. So the first example, what we did was we didn't know about pH. We couldn't calculate pH, but we were able to construct PCPH. We had a complex of mercury with 2 different ligands. The second one, we had the whole picture of chromium, only complexation with ammonia, and we were able to calculate pH by basically logically simplifying, mathematically simplifying the equations. The third one is quantitative. We're not going to solve it qualitatively. This is basically a more realistic scenario that we have out there. It's speciation of chromium. So let's say we have a sample prepared by adding chromium nitrate, similar to the previous case. Also, we add sodium sulfate. So let's say just we add it to the solution. And then the sample is exposed to a gas phase that contains both CO2 and ammonia. So it's not all ammonia, but CO2 is also involved. We want to ignore the complexation of chromium ion with hydroxide, and we're also ignoring any mixed ligand complexes. What we want to do is basically evaluating all the dissolved species, so the species that we have in the system. So this is again more on the qualitative side. So let's say if I start from gas-liquid equilibrium, because this is an open space, and we have 2 different gases in the gas phase that could exchange or interact with the liquid phase. So we have first gas-liquid equilibrium. So when we have ammonia in the gas phase, it forms ammonia or brings ammonia to the aqueous phase. So basically that's one species that we have in the solution by introducing from the gas phase. Also we have CO2 in the gas phase. It also equilibrates with CO2 in the aqueous phase. And we know once we have CO2 in the aqueous phase, it basically turns into H2CO3 in the aqueous phase. So by exposing the gas phase to the liquid to the atmosphere with CO2, we're introducing carbonic acid in the liquid phase from the open system lecture, gas-liquid equilibrium. So that's what we're bringing to the system. It seems we're also adding 2 salt to the system. So we have salt, the solution. So we have chromium nitrate. So we're introducing chromium 3 plus 3 nitrate. So by dissolving this, we're introducing nitrate, and we're introducing also the chromium ion. So it would be chromium and the nitrate. Same thing for sodium sulfate. 2 sodium plus sulfate ion. So now we introduce these 4 species to the system. So once we have, all of these species, once we have all of this in the system, then establish equilibrium. The first kind of equilibrium is acid-base equilibrium from chapter 2. So acid-base. So from acid-base equilibrium, we know ammonia is in equilibrium with ammonium, with ammonia and proton. Basically, this will be introduced. Also, once we have H2CO3, it dissociates to bicarbonate. Once we have bicarbonate, it dissociates to carbonate. So we basically introduce these 2 ions. As always, we have also water. So H2O, H plus plus OH minus. So H plus and OH minus always there. So beside this one, we have also this acid base can also be interacting with the metal. So the metal that was introduced by the solution of the salt. So now this guy can also interact potentially with a few of this one. So the complexation equilibrium. Based on the table, we know chromium can complex with up to 2 ammonia. So ammonia to form chromium ammonia 3 plus. So that's 1 species. The other one is chromium 3 plus can react with 2 ammonia. Again, based on the table, all the possibilities. Chromium ammonia 2 3 plus. And also chromium 3 plus can also complex with sulfate. Again, based on the table. This would result in chromium sulfate plus. And this would be the new species. This would be So the possibility of forming these complexes was guided by the table and the fact that we have ammonia and sulfate in the system. So by exposing that salt, that liquid with those two salts with that atmosphere, we're getting all the species. So we have like a very long Excel file if we want to do the calculation. Two types of interaction we haven't talked about. That's one is precipitation, one is the redox kind of interaction that will be added basically to this one. That's why you get more and more species in the system. So to wrap up, what we talked about here was basically more ligand. So previously we had metal with water and hydroxide, but now we basically talked about metal with ammonia, with, for example, Cl minus, and so on. But the concept would be similar. Whatever we learned in the first lecture, it can be applied also here. And it could be two at the same time, but independently, not together, not a mixed ligand. We also constructed a PC-pH diagram. Also, we solved for solution pH for metal complexation with different ligand. And in the next lecture, we're going to talk about precipitation and dissolution, part 1.